Okay.
Okay, so I can start. Is it okay for me to start now, or should I wait for something else?
Yes, go ahead.
Okay, great. So, hi everyone. Thank you for coming. Hello from distant Israel. Today I'm going to talk to you about projects I developed and researched at Checkpoint. This is the company I work at in Israel. The project is called DeepVBA. It's a graph convolutional network approach for malicious code detection. So just a little bit about Checkpoint before we start, to those who are not familiar with the company. Checkpoint is like it's the leading global cyber security company in the world. Over 100,000 customers.
Yeah, can you speak a little louder?
Yes, sorry. Can you hear me better now?
Yeah, that's a little better.
Okay. You have that like an echo when you talk. I don't know if you notice that. Anyway, it's a global leader in the cybersecurity community. Over 100,000 customers in more than 88 countries. A lot of partners. It's been traded on the Nasdaq since 1996. It's a leading innovative leader in the AI for cyber security community. It's protecting one of the world's largest organization, McDonald's, Citibank, Bank of America, AT&T, JP Morgan, and more. Checkpoint focuses on prevention and not detection, and that's basically why we developed this project, because my project deals in prevention. You don't want, when you deal in detection, it's basically already too late. You're detecting that something happened. It is much better to prevent something from happening at the first place, or starting to understand the what exactly happened and detecting the attack and then containing it. It's a far difficult task to do than just preventing the attack altogether. So the entire solution of not only my solution, but the entire the solution of what Checkpoint advocates for is that it's prevention first. Okay, so it's the only effective way to stop threats, cybersecurity threats in general. So that's just a little bit about Checkpoint. They told me not to talk too much about Checkpoint because they don't want this to be a sales pitch. So I really tried to keep it to a minimum. I hope I did okay. That was just like a 1 minute about Checkpoint. So just a little bit about myself. My name is Dor Livne. I received my bachelor's degree and master's degrees in electrical engineering. And chance you can raise your mic volume. Okay, I can try with the settings. Let's play a little bit with them. Let's see, microphone. I don't know if I want to touch these things. Is that better? Is this anything better? Is this okay? A bit. That doesn't help me.
You're good. You're good on my recording. Go ahead.
Okay, so just maybe crack the volume up at your side, because I'm basically screaming here. I don't want to wake up my baby, so my newborn. So I'm sorry for not screaming into the mic. I'm trying to hold it like this. Maybe it will be better. So I think now it's like a lot better because I'm really talking into the microphone. So coming back to the presentation. So my name is Dor Livne. I received my bachelor's and master's degrees in electrical engineering from Ben-Gurion University. I'm currently working at Checkpoint as a data scientist for the past a little bit more than a year. My objective at Checkpoint is to research and produce novel and efficient ways to detect malicious attacks by utilizing the source code, among other things. Actually, one of the ideas that I worked on, which already passed POC and is in final stages into production, is the DeepVBA solution, which I will present in this presentation. So the agenda for So the agenda for today is, first I'll go over the history of what is VBA macros, what are macros, to understand the domain of the source code that DeepVBA works on. We'll explain a bit about the motivation, why should we prevent the attacks and not detect them, and we'll showcase a really famous VBA-based attack called Emotet, which really did harm in the world, caused a lot of harm in the world back in 2014, and basically up to today, still around. Works as a software as a service for criminal masterminds. We'll talk a little bit about current approaches, not a lot, just go over how usually this static code analysis is done. Then we'll dive deep into the DeepVBA approach, talk about the objectives, the overview, features, the explainability of our approach, and the data augmentation we use to train our models. And then we'll summarize. So history of macros. So macros have been around for quite some time. And basically from Office 95, there was like a simple or yes/no prompt to enable the macros. So first off, what are macros? So if you have like an Excel sheet, it's like the most common example that I can think of. If you have an Excel sheet and you have like a column and you want to sort the column according to the values in the column, you can create a macro that will sort the values in the column. That's the typical use and common use for VBA macros, but that's just the most simple way to use the VBA macros. You can also use it to create a shell object and connect to the internet and download stuff from the internet, and from there the imagination only limits you. So back into this slide. So when Office 95, 97 started to enable to run the VBA macros, all you had to do is just to click yes or no on the enable macros prompt. That was really easy to social engineer the victims, to execute the macros. All you had to do is just accidentally click on the yes button, and voila, the VBA runs. So that created like a macro, something called a microvirus era, with a lot of famous VBA macro-based attacks from 95 to 2003. Then in Office 2000, the on-site macros were disabled by default. That caused the VBA winter. Attackers preferred exploits to VBA spear phishing attacks. And then in Office 2010 and 13, 16, 365, you have what you are familiar with today with the enable content, which is usually now what Microsoft thought would solve everything, and that is why it brought back VBA macros, because the attacks are now sandboxed. And what I mean by sandbox means the attacks that's called the dynamic analysis. It means the code is running and executed on a sandbox machine. And then during that emulation stage, if an attack happens and the emulation knows how to detect it, which is also not a simple feat, and the file is basically prevented from running on your actual machine. The problem with dynamic analysis is that it is very easy to avoid, because all you have to do is just not run the code for like a couple of seconds or minutes, and then the sandbox, because it's an expensive procedure, it doesn't have all the time of the world to run your code. So that's like just the simplest way to avoiding emulation. There's a ton of other approaches to avoid emulation. So that's why dynamic analysis is quite accurate when it actually emulates the attack, but you always have to have another defense mechanism, which is static. Just looks at the string of the code and tries to understand what is the intent of the code from the string alone. And that, for those who deal with natural language processing, they are familiar with this feat. It's not an easy feat. It's not an easy task. So from 2014 to 22, VBA macros came back. 2014 was the premiere of Emotet, which we will see soon in this presentation. It's basically it's frequently used as a first stage attack, first stage to the malware. Basically, it just downloads the attack from the web, adds persistence to it, and then the attack proceeds to stage 2, stage 3, stage 4. And from that point on, from stage 2 forward, it's really hard to contain the attack because the variance there is just, every cyber attacker has its own approach. In April 22, Microsoft issued a policy change, which they, as far as I know, they still haven't rolled in. But basically, it just makes it harder for the attackers to social engineer the VBA attacks because it's no longer just click on the enable content. It's like a two-stage procedure to run the macros. So it remains to be seen what will happen when this policy change propagates through all Office versions, I guess. So what is our motivation? So VBA macros are used as a first stage attack with malware. Most VBA macro attack use different and various techniques to prompt the users to enable macros, making them vulnerable to the VBA code that runs automatically. That's the point with VBA. It's like an event-based language. So when the document opens, it runs. When the document closes, another portion of the code runs. And you don't have control over it. The only control the user has, or the target has, is whether to enable the macros or not. Once they enable the macros, once you enable VBA macros, when you open an Office document that you downloaded from the web, or you got from someone, if someone sent you via email, you're completely helpless. So the current antivirus engines are just not enough because there are too many macros every day. And it's impossible to catch up with signature-based solutions, which is what the cyber community usually use to protect their clients. They use analysts to sign attacks, and then they search for these attacks. Okay, yes, thank you, David. So sorry, the chat is popping up in the middle of my screen. Kind of hard to follow through with this presentation, but I'll make an effort. So most malicious VBA macros are not detected due to this common approach to all cybersecurity communities. A signature-free model is needed to basically give answer to these rise in VBA macros. Basically, just to do static code analysis to detect malicious intent. It's something that the cybersecurity community needs, and it's something that is on the rise in the previous years, like everything else in the world. With the emerging of the new powers of AI, it leaks into all domains, and cybersecurity is not unique in this case. So before we dive into the deep learning and AI and data scientists, let's put the hat of cybersecurity researcher for a second and try to understand what are the four main what are the indicators that we are looking for with our eyes when we see VBA or basically any source code that triggers the malicious signal in our minds. So there are four main indicators in the VBA domain, and I'm sure it extends to many other programming languages, and that can be extracted from the code. You don't have to run the code; it's enough to look at the code, maybe look hard at the code. It's not like it just jumps out, but you have to look at the string, look deeply in the string, and then you can see four main indicators. That's the four main indicators you need to look for. So one is that the code is auto-executable, and two, that the code needs to drop a payload or inject the code into some process. They also need to if they download the payload, you want to see maybe not explicitly, but implicitly that they execute that payload. And it's usually obfuscated to hide their intent. Because if you go with if you want to detect and not prevent, then obfuscation is your friend. Obfuscation is the friend of the attacker, I mean, because then it's really hard to understand what the attacker did and how to contain the attack once you detected that something happened. So a lot of attackers use obfuscation to hide their intent and what they're actually doing. So I guess that if you want to, have like a Boolean equation for what is a suspicious VBA, or I'm using the word VBA a lot, but it's not limited to VBA only. It can be any source code, I guess. So suspicious code might be something that it's auto-executable and one of the other three indicators. That's like a really suspicious sample, but it's not limited only to this Boolean equation. It's just something that a security researcher might look for when parsing VBA.
So can I ask a question real quick? So are these considered one-click exploits? Are you familiar with that term?
It's a bit hard to say because it sounds like you're like lowering their complexity. I guess that if I have to summarize all the VBA attacks that I've seen, it's usually the first stage in a multi-stage, very complex attacks that sometimes uses a command and control. It just opens a command and control server, and that can control your computer and just encrypt or ransomware and all that. But yeah, it's just it's a one-click. Once the user enables the content, the exploit commences. So I guess it's you can say it's a one-click exploit. Yes.
Well, yeah. Are you going to talk about any zero-click exploits?
No.
Okay.
No, because the user must enable macros. So
thank you for answering my question.
Yeah. So the user has to click something to enable these, especially if he downloads it from the web. Maybe if he downloads it, if the attackers I don't know, took control of some computer in the organization, then send email from that computer to other people in the organization. So it's something called like a lateral movement. Maybe then you don't have to enable the macros, but I'm not so sure. I think that when my friends send me emails with word attachment or something, I still need to enable macros. So yeah, it's a one-click exploit in any case. So let's get more intimate with this domain with an infamous example. One of the most popular VBA macros-based attack is called Emotet. Emotet was first identified in 2014 as a banking Trojan that steals sensitive and private information. Recently, it is being used as an infrastructure as a service at the black market for delivering malware. The most common entry vector of Emotet is spear phishing email with some sort of attachment. So here's just a bit of titles I picked up from various blogs and from the news, just to emphasize how big Emotet was back in the day. It took like the Europol had to intervene to contain this attack. It cost billions of dollars to a lot of banks. And how it works is first lures the victims, and we will see how. It installs, once the victim is social engineered to that one-click exploit, the attack installs itself, infects the computer and other computers in the network. It changes itself, it's polymorphic, it's persistent, and all the bad things an attack can be. So just please protect yourself from macros. Just don't run attachments from people you don't know, and basically just don't enable macros just blindly. Think before you do that. Okay, and if the email has like a sense of urgency, don't trust it. Okay? Don't be a sheep. Okay, so here is an example of an Emotet spear phishing email. Again, a sense of urgency in the email. You have to pay something. What I have to pay? I have to pay something. The bill is with the interest rates today. I have to pay it. I can't wait anymore. So you open the document and you enable the macros because the document says if you want to look at my content, you have to enable macros. And the sense of urgency social engineers the victims to just click on that enable content. So easy. So once the user enables content, the code launches. So what is the code of, how does emotet code looks like? It looks like this. What is happening here? It's, as you can see, it's highly obfuscated, very hard to analyze what it does. With the human eye, we can't really understand what's happening, but if I did that work for you. So you can see it's auto-executable. You see it with the function document open. Document open means when the document opens, the attack commences. And you can see it calls the function, I don't know how to pronounce it. So we already have two triggers. We already know it's auto-executable, and we already know it's obfuscated. Okay, so after a cumbersome manual analysis, which de-obfuscated the code launches a malicious process that runs a PowerShell code, which is included in the heavily obfuscated VBA. Okay, I won't get into what's happening here, but it's bad. Okay, so again, the other triggers are triggered as well, but to get to those triggers, we had to allow our human eye to understand that these triggers are initiated. We had to de-obfuscate the code. We had to do some cumbersome manual analysis. We can't do that on runtime because the inference needs to be quick and it's not scalable. So what can we do? How can we still detect these two triggers through obfuscated code without de-obfuscating the code? So basically, we can rely on that some API calls cannot be obfuscated, as we will soon see in our DeepVBA analysis. And one of those examples are the create and the get object. Those are APIs that cannot be obfuscated. So we already know that the code creates something. It creates an object, and you can probably also detect other important triggers that maybe the deep learning system can detect deeper patterns that the human eye cannot detect from the code alone. To get a glimpse, maybe implicitly, of these triggers. So to summarize emotet, the initial vector of the attack is the VBA macro code, which is attached to our malicious document. The VBA macro runs a PowerShell process that downloads an executable. That's already in the emulation step. You won't see it in the static code analysis. And the executable eventually opens a backdoor for criminals to install other type of malware. Okay, so that's like emotet really in 5 minutes. So current approaches to detect malicious VBA are based on the code. They usually use handcrafted features or handpicked words combined with some sort of a basic classifier. As you can imagine, these things are just not enough. You have to let deep learning do its thing and trust natural language processing to have the power to detect meaningful patterns that any analyst can prepare. Of course, it is good. It is always helpful to help your neural network model learn by helping it with significant and important features, as we have done in this work. But not only, we have not limited ourselves. We will see exactly what I mean by helping the model learn, by giving it significant features, and by maybe letting him try by himself. We tried both approaches, and they are both embedded in the system. Because maybe when you feature engineer something, you might lose information in the process. So one of the biggest disadvantages in those static code analysis techniques is that they compute the code as one single chunk. And as you saw at the emotet examples, when I intentionally presented the emotet code as one single chunk, because I wanted you to like, okay, what is happening here? I don't understand anything. And exactly the same thing happens to a deep learning system that tries to read the code as one single chunk, because it's just too much noise. The string is too noisy, and you're ignoring, and the system ignores the important connections between the functions. So the hierarchical information of this function calls this function, and that function calls that function. That hierarchical information must be kept and maintained and encoded in the deep learning system in order to perform valuable programming language processing. Not only malicious code, not only to detect malicious code intent or semantic information that relates to malicious intent, you also want to do that when trying to understand what the source code do. Okay? So a lot of attacks use evasive maneuvers. where they just add meaningless functions to evade detection. So using that hierarchical representation helps us to minimize the noise in the input, because the model learns that some functions are just not important. It's just obfuscated functions or redundant functions that do nothing, just while for 5 seconds and continue, something like that. So now we put back the hat, our data scientist hat, after we removed our cybersecurity researcher hat, and now we know what triggers we want to detect. But those are the 4 triggers. That's we want our features to emphasize these 4 triggers, and we want to identify those 4 triggers implicitly or explicitly, again, of course, by overcoming non-invasive maneuvers, minimizing the noise in input, being a signature-free model, and also it's important to be a lightweight model. We can't just use GPT chat on every document our client receives. It will cost a lot of money and a lot of computational power. So we have to find a lightweight solution that the latency won't be above hundreds of milliseconds. Okay, that's like our cap. So the DeepVBA is also lightweight. So it's not more than a couple of megabytes for a model. DeepVBA utilizes the call graph structure and the VBA macro code to classify the VBA macro as malicious or benign. Okay, so pay attention that our call graph representation does not we do not diminish any information from the source code. We still use the entire function code minus the comments. Maybe normalize it a bit, but we wanted to give the model the entire function code for each function, so it can learn for itself what are the deeper patterns that are important in order to detect those suspicious triggers. And we use the call graph to basically give the hierarchical information and to help him understand what the code does. And we also engineered some important features that I think helped us a lot. I know, helped us a lot to identify those triggers, and we will see them in the following slides. So I guess this is a good place for questions. If anyone has any questions, it's a good place, because from now on we're starting to get very, very technical.
I think there's some questions in the chat.
Sorry, I could not understand what you said.
There are a couple questions in the chat.
Oh, in the chat. Okay. No, got it. Chat. Okay, I see. Can someone help me find them? Because I see FFA told the progress website that issues developed in 3 AM. Not sure it has anything related to me. Maybe Andrew Donahue is raising his hand. Did I pronounce it right?
Yeah, I have a question. I always thought that the default macro settings of not running signed macros stopped a large majority of the phishing attacks. But you're you seem to explicitly state that that is not the case, that there are a lot of phishing attacks that are coming through with unsigned macros and that are being executed. This sounds like a failure of Office administration. So I'm confused. I thought Microsoft had closed this huge hole like years and years ago.
So yeah, as I showed in the first slide of this presentation, before 2014 they did have that policy change when the unsigned macros were disabled by default. But in 2014 they enabled the sandboxed approach. Well, the user just needs to enable the content to run the macros, and the macros are actually executed in a sandboxed environment. But as I stated back in that slide, it's not enough. Attackers find a way to avoid sandboxed attacks. Of course,
so the sandbox isn't actually very protected. It's not much of a sandbox. It's sort of a leaky abstraction.
It can be leaky. The attackers needs to be a little bit creative to avoid it. It has to detect it's in a sandbox. It has to detect maybe have to perform some really weird stuff to avoid that. It's not that trivial to avoid the sandbox, but it's possible. It's been done, and today you can still see attacks that are based on these VBA attacks. But in April, Microsoft issued a policy change. So I guess they're trying to fix that hole, but they also want to keep the VBA macros operational. They want people to use it. So it's a spectrum. You have to understand where it's the best. How much you want to protect your customers, but you also want to give them free of use. To allow them to use your features as they like.
Okay. Thank you.
No problem. So I guess it's kind of hard to understand the questions from the chat because there's a lot of chatter here. So if someone has a question, please just barge in. It's okay. I won't get insulted. So DeepVBA uses the VBA to graph Python library. It's an open source library that is able to create a call graph on the VBA macro. And VBA to graph is a Pythonic open repo. Yes. Greg Freeman, you have a question? Sounds like you're in a spaceship or something.
Yeah, Greg, mute yourself, please.
Okay. VBA to graph marks the functions that are launched automatically and highlights potential malicious keyword APIs. For Emotet's case, it is more friendly and more easy to observe him using the VBA to graph. Isn't that a lot? Is a lot prettier in his call graph transformation. And you can see that the document open is an auto-executable function that all the subgraph that originates from that root function is also auto-executable. And you can see here in this keyword sequence underneath the function name, you can see all the APIs that cannot be obfuscated. So you can already see how you can use this VBA property. And basically, all programming languages have those APIs that cannot be obfuscated. You can use these API keywords to maybe detect the intent of the function, but that we discovered in our research that that's not enough. You need to use the actual code to really understand what the code is doing, and that is exactly what we did. We also use this keyword sequence because sometimes the functional code is really, really long, and the keyword sequence is like a compressed version of the code, which allows us to get a glimpse or maybe a whiff of what this code, what this function actually does. Okay, so that is our input representation. It's not all our features, but just how we go from source code to graph. If something is stuck. What's happening here? Okay, PowerShell. This is not a good application. So here you can see in the DeepVBA approach, you can see the overview of our framework. I'm sorry that this slide is not really pretty, but you have to make do. So first we have our call graph. And now the issue I stumbled upon is that each function has a different length. And I wanted to exchange information. And when we're talking about exchanging information between two mathematical entities, we usually have to bring them to the same dimension. So how do we do that? We used our node embedding module. Our node embedding module is the powerhouse of it uses the most of the computational complexity of the model is in the node embedding because it basically does the natural language processing. It processes, it extracts the features, it multiplies all the matrices, and it's basically the dominant consumer of computational complexity in the DeepVBA approach. So the node embedding, what it does, it basically creates it encodes each function into a fixed size representation, and so we'll come back to this slide. It's going to follow us through the following presentation. Don't worry, we'll come back to it and we'll talk about the other modules. So I just want to dive in a bit into the node embedding module. So as I said, the node features, they are processed by node features of the function, of course. Those are the function code and other function features that I will maybe give you a few of them. Outputs a fixed size representation feature vector for each function. As I said, after each function is represented by a fixed size feature vector, DeepVBA can aggregate these node vectors using a graph neural network architecture, basically a graph to one architecture, with an attention to emphasize the malicious nodes for graph classification. That's basically the overview of the previous slide, but we'll come back to it and it will be clear, so don't worry. Okay, be calm. The node features consist of also handcrafted features, such as the suspicious code keyword sequence, as we already saw, and also the code token sequence. So for those who do not know what are tokens, so the code token sequence help us to detect significant signals in a nifty way. One of them is obfuscation, and I'll explain. So the tokens are created by training a byte pair encoding tokenizer, which is trained in a similar fashion to Huffman compression. Okay, for those who are familiar, for those who do not read about Huffman compression, you have to know it. So basically, what it means is that frequent substrings will be given a token, and non-frequent substring will not be given a token. What I mean, let's see an example. So here we have a function code that I just sampled from my database. It's malicious code. And you can see here the tokens that are created from this function, the token sequence, and you can see that it's usually base vocabs, right? It's just base vocabs, GU, O, Q, because the code is obfuscated, and of course, obfuscated is not frequent. But you can see glimpses of frequent substrings like air, at, call, NN. Those are more frequent substrings in our database. So that's how you can use byte pair encoding also to detect obfuscation, just by understanding the compression of the string. And that's like a nifty scalar to detect obfuscation. Just because a scalar, you can understand the obfuscation signal in your string, which is a powerful feature in our a powerful and efficient feature in our research. But also we also use the token sequence itself because we want to give the model the option to learn deeper patterns that we can ever engineer.
Dor, have you guys ever thought of looking at syntax trees? I mean, once you're tokenizing, I mean, obfuscated code still makes syntax trees to execute properly, right? And it seems to me that the syntax tree is actually the code. And so when you're just looking at tokens, you're not really looking at the code. You're not looking at what's intended. You don't have the logic.
You're absolutely right. It's much more. It is much better to understand the code intent or the code meaning using the AST, the abstract syntax tree. The issue here is that we didn't have any compiler that can create that abstract syntax tree, and in Checkpoint, in my team, in the CTO group, time is money, and we didn't have time to build a compiler to build the the abstract syntax tree for the VBA source code. So we just used what we found, and what we found is something that was developed also in Checkpoint, the VBA to graph library that can create a call graph, and we saw that it's enough, and it's a good first step, and also. When you use abstract syntax tree, it might be too much information. It might be too much. It might be too much noise. The call graph, we found it to be a good in the middle representation that also gives you the hierarchical information, but not overwhelms the model with billions of edges and nodes. Okay, does that answer your question?
Yes, it does. Thank you.
Yeah, but we I actually first looked for how to create an AST for the VBA, but then I gave it up because I just didn't find it. how to do it in a quick way. But other languages that have a compiler already and you can create AST, you can basically just project this approach on the AST. It will be similar. Okay, you will just not have the code token sequence and all that, but the idea will be the same. Probably have to have a really strong machine, I guess. Because here we're just limiting the code token. We have like just 1,000 tokens. So if the function is really long, we don't get to the final sections of the code. That's just a technical limitation at this moment. So as I said, that the compression ratio that we can calculate from the token code, from the code token sequence, that scalar, it can be used to detect a good signal of obfuscation. You can see here during our exploratory data analysis that we did on that feature, you can see that in the benign distribution, the compression is pretty strong. We are able to compress the benign samples better than we can compress the malicious distribution. And in the violent plot, you can see two blobs in the malicious distribution. You can see here the blob of the obfuscated code, and you can see here the blob that says, wait, these functions are not obfuscated. What is happening here? So this part exactly proves my point that there are evasive maneuvers taking place in the malicious domain in order to blindside other suboptimal static code analysis by using benign functions to hide the real intention of the malicious function. So just like a cool example to show off how a single scalar can be a really pretty important feature in a really tough task, such as programming natural language processing. Okay, Tzvi asked the question, could malware creators just create large padded with non-executed code function to bypass your detector? The relevant tokens will be obfuscated by added load. If I understood your question, so you say if the function itself will be really long, will it be enough to bypass my detector instead of like a lot of functions? So instead of a lot of functions, just a single long function. Yes, of course, it will reduce the signal in my model. I haven't seen it too much in the wild because it seems to be an interesting idea, but still the obfuscation signal there, I imagine the compression ratio of that function will still be pretty high because it will not, because some of that code will not be obfuscated. Maybe the code token will not reach it because the code token is limited. So that's just a limitation. And I'm not happy with it. I will happily have a huge machine to tokenize the entire function, but that's not the case in my case right now. But for that case, we use the keyword API sequence. The keyword API sequence is not truncated, and it's usually long enough to encapsulate any function that I've encountered. So for that long function examples, the keyword API sequence is coming into the rescue, because if there's some malicious intent in that function, you will probably see some shell, you'll probably see changing of the registry and stuff like that happening in the API keyword sequence. It's not perfect, but every model has its caveat. But I thought about it when researching it's not dominant in the data, but the keyword sequence should help with those type of cases.
That makes sense. Thank you.
So just looking at the tokens themselves, you can see that there's a huge difference between the most frequent benign tokens and the most frequent malicious tokens. As I said before, the malicious tokens are usually comprised of base vocabs. You can see B, C, F, D. Those are the base vocab that comprise of the malicious distribution. And in the benign distribution, you can see normal English-based words. They're not trying to do anything weird. So there aren't any weird tokens. On the other hand, on the right side, on the malicious, you can see if you You can see the base is like the token. Just, okay, I understand the word base is okay, but the base is.
Oh, are we muted? Oh, sorry about that. We have a quick question for the audience.
Sorry, like a really, really basic,
Okay,
naive,
sorry, I just ran forward.
Microsoft/VBA question. Like, so when I'm thinking of a macro executing, is it? I don't know anything about Microsoft OS, but is the user/server/system account that's executing the macro? Does it come with like? So I'm assuming there's like privileges that it has and has not. So how many of these attacks depend on like user engagement and a privilege escalation, or am I mistaken in thinking that the privileges associated with a macro running are gated to begin with? So just like a basic like context question about how macros run and what they can and cannot do by default.
Well, macros can run shell. They can download attacks. They can just what they usually do. They do not. You don't see the entire attack in the VBA macro. All the VBA macro has to do is to download an attack from the web and run it and add persistent to it. It's pretty easy. Just contact an HTTP, download an executable, or download something, or download a PowerShell script from some repository, and then schedule a task to run it in like 5 minutes. That's all you have to do, and then the variants of those attacks are limitless, okay? Because the PowerShell can do something else, and maybe run something else, and maybe override DAMZ. Really, I can't even begin to cover all the options once you can just download and run something from the web.
Okay, thank you.
Hope that explained it.
So attacking this one pattern cheaply can be really useful, even if you have multiple models deciding if it's malicious.
I'm not sure I understood the question.
I mean, your model could become just a feature to a larger model that does more if it's cheap.
That's the idea. It's not a standalone model. It's a part of a larger protective mechanism that also does dynamic analysis. It also signs the attacks with analysts. This cannot alone stop all the attacks. Of course, it's just a way to do static code analysis, which is one of the pillars of cybersecurity with files that are downloaded from the internet. It's such a narrow window to the cybersecurity world because there's the endpoint and the gateway and the and packets and networking and all that. And I'm just talking about detecting from Microsoft files. It's a very narrow window in the cyber community world, but it's an important pillar because static code analysis in VBA can also then be used. This approach can also be extended to other programming languages. It's not that hard to imagine how you can create call graph or AST as suggested earlier and use the same ideas to protect from, say, PowerShell. And almost all attacks use PowerShells, fileless PowerShells. So if you can detect, okay, there's a PowerShell script that is being run or is going to run, I'm going to run a PowerShell script now, you can prevent it from executing by statically analyzing it.
So if I may ask again, at least in the JavaScript community, there's a very common practice of minimizing JavaScript libraries, which basically is obfuscation and shortening tokens to single character names and all that sort of stuff. And does not seem like that's a common practice in the VBA land. But if it ever became such a case, would it take your signal away that it's clear that everyone who is malicious obfuscates or minimizes just to make life a little bit more difficult? Bandwidth isn't free, never has been. It's freer than it used to be. So maybe it's less of an issue, but minimization is still a big deal in JavaScript land. So I'm kind of confused that the signal is so strong here.
So in VBA, obfuscation is a strong signal, but it's not this signal that we're looking for. We're not an obfuscation detecting machine. You just can see it's a strong signal in the VBA domain. In other domains, that obfuscation is used to hide the patterns, or as you said, to minimize the memory stamp to code. We have to do our research. We have to understand what are the features that comprise of a malicious code. Maybe when JavaScript is minimized, you can't really do static code analysis. Maybe in those cases you can't. You have to rely on dynamic code analysis. But maybe when JavaScript is not minimized, we just look at that subdomain. Maybe there we can do something important with static code analysis. It's important to understand what can we do and what are the problems, and to do good research and understand the domain that we are working on. Unfortunately, I haven't had a chance to work on JavaScript yet, so I can't really answer that question. But again, good research to understand how those attacks, how JavaScript-based attacks look like, what are common among them, what are the indicators to look for in those attacks, and then you can use this idea. Of course, if it's minimized, and I think I saw one of the examples you're referring to, just a long line of byted code when the JavaScript is minimized. I guess, in my opinion, in those cases, there's not a lot you can do with static code analysis. You have to run the code and see what happens, unfortunately.
Thank you.
No problem. So we talked about the node embedding, all that was the node embedding module. Uses the code tokens, the keyword sequence, other hand-crafted features that are not really important, like how much message boxes there are or something like that. There also is a strong feature, is the node auto-executable and other features. And it encodes the function into a fixed size representation. And once the code is once each function can communicate with other functions, we can use the graph neural network to basically aggregate the hierarchical information and exchange information using the message passing technique of the graph neural network to exchange information and share information between the nodes. And basically what the graph neural network does, it maintains the same graph structure, but each node communicates with its neighboring nodes. So the communication, based on how much layers you have, the communication spreads exponentially of the information, of course, between the nodes. Let's just look a little bit about what is the message passing in the graph neural network layer. So it's a pretty simple equation. I'm not sure how much time I have. I think I'm already over that, but
yeah. Can we
I'll speed it up.
Yeah.
Sorry
Thank
about that. You can refer to the web to understand. Let me know if I have 10 minutes before. Okay, it's important because we might get.
Can we give you like 12 more minutes just for the sake of the speaker?
12 more minutes is a lot. I can be laid back.
Thank you.
Okay, so basically here you can see that the for each node we're multiplying a fully connected layer with its neighboring nodes, and then we aggregate by just summing it all the node embeddings of the neighboring nodes, including the node itself. If you can imagine, there's like an edge to itself, and we're dividing it by the degree to normalize. If there's a node that is highly connected to other nodes, we don't want it to totally control the entire graph representation. So you have to normalize it by the degrees of the nodes. And that's like the most simplest way to do message passing in graph neural network. There's much more complex ways to do that with edge features and all that. But I won't get into it in this presentation. So that's like the message passing on one leg. I invite you all to read about graph neural networks. It's an incredible technology. So now we have a graph, but we want a malicious signal. We said at the beginning of this presentation that we want to graph to one architecture. So we have to encode and aggregate all our graph structure, all our nodes into a graph embedding. A node embedding needs to be transformed into a graph embedding. Now, how do we do that? We can sum them, but then we're not avoiding and minimizing the noise in the input, because then evasive maneuvers can be used to dilute the signal in the nodes. So we want to use an attention layer that can help understand, that can help us build a distribution over the nodes that we can use to basically do a weighted sum based on that distribution. So that is the job of the attention, the hierarchical attention in this, to be more specific. So as I said, it outputs a probability distribution over the nodes, and we can use that probability distribution to perform a weighted sum. And we believe that the attention learns to avoid meaningless and disconnected nodes by giving them smaller weights. And we actually have an example of it, specifically on the emotet example. So here we can see emotet, clean, I haven't touched it. And you can see here underneath the functions, you can see the weights, the distribution in percentage of each function. In this part, it's uniform because all functions contributed the same to the attack. A document open is auto-executable, and these functions are highly obfuscated and also communicate with each other. And one is operating the shell, one is creating the object. So in this sample, you say, okay, it's basically uniform. The attention didn't do a lot. But what happens when I add benign functions to the mix? So I added benign functions that I wrote, so I know they weren't in the data. Just sorting out some sort of column that I invented. And you can see that the attention mechanism learns to give smaller weights to benign functions and higher weights to the malicious attack. The attention helps us explain what is the source for the malicious signal. That's like a cool side effect of the attention layer that can be used to explain our deep learning system. And we take pride in this feature. It works it's pretty awesome. Basically, imagine if you have like a really big graph, you can like pinpoint what are the functions that caused it to be malicious, and it helps to explain what are the patterns that our model is searching for. So just
hey, can you start just giving us the end of it, and we can do a little bit.
Summary.
Thank you.
Thank you. So summary, you get an email, you enable content, the code runs. You're gonna have a bad time. Wait, but if you have our static code analysis protection techniques and of course surrounding defensive mechanisms, you can extract the code graph from the malicious code, use our DeepVBA code graph approach, and prevent this code from ever running. That's just a summary of the basically of the DeepVBA code, the DeepVBA approach. So this is a good place to stop. And if you have any questions, might be a good place to stop and answer these questions.
I have one question, George, if you'll allow it.
Yeah, go for it.
Okay, so you were showing all those nice techniques to do code analysis. Today, however, and I'm not talking about VBA, let's talk about Python. Python, there are all sorts of like linters and all sorts of other tools that help you sanitize your code. And usually they bring in all sorts of errors and stuff like that. I was looking at those examples of VBA code and I was thinking, if I had a tool like that that tells me all those warnings and errors about all those functions and things that I'm doing funny, then maybe it will help you do the scoring. But this is again for other languages, like if you like find malicious code in Python, which is, did you think about it, or it's an open question?
Yeah, when we started this project, we just basically wanted to build a smart static code analysis model. Later on, it became something that was projected on the VBA domain because it was the easiest thing to do and the quickest thing to do. And we already had the data, we already had the code graph repository that created the code graph for us. So it was the easiest thing to do. But the ideas and the approach, they are not limited to any type of programming languages. I'm not the first, and I'm actually not the first one to use core graph and graph neural network in the deep learning community. I haven't. I'm not the first one. I think I saw some works doing that to detect. You can see like a code belt, graph code belt. They do it to like understand what each function is doing, what is their meaning, and they do it over several functions. They basically use the comments and they try to predict the comments of the code. It's something weird like that. But basically these ideas are around and they are used for multiple approaches. Of course, for each different problem or research direction, you'll have to do the research. You have to put in the work. It's not a plug and play solution for any code problem. Of course, it's directed into malicious detection.
Thank you. Hey, Mike, I see you have your hand raised, but I'm going to ask if you could save your question for maybe after so that we can move on to the other speaker. So we just have time for him as he's in person. He might need to leave.
I'm not sure Dor can stay that long. It's pretty early here. So if you can.
Okay.
You can send it in email now. Answer it tomorrow. Or your middle of the night.
Is it like a under 30-second question?
Yeah, it should be very quick. If this is commercially available, have you seen anybody try to basically by hand make an adversarial network?
No, I haven't.
Okay. That'd be interesting. Not for you, though.
No, I haven't seen anything like that being tried on this network. It's not open source, so I don't know if that was the question. But no, I haven't seen anything like that. But I'm familiar with adversarial neural networks, but I haven't seen anything in the malicious source code static code analysis department.
All right, cool. Thanks.
No problem.
All right. Well, thank you, Dior. Let's all give him a round of applause for that talk.
Thank you.
Might not hear it, but there's a lot of applause here.
Thank you.
Get ready for our next speaker, Jonathan. I'll just set him up over there.
Thank you for having me. I'll be leaving now. Bye-bye.
Thank you.
Bye-bye.
Thank you, Dor.
No problem. Bye-bye.